Hello everyone and welcome back. My name is Mr. Kovalt, and in this video I'm going to be going over representing different molecules. I'm going to go ahead and draw Lewis dot structures and show you how they're hybridized, how the atoms are hybridized, as well as how the unhybridized orbitals are working. And so basically we'll be applying VBT, which is valence bond theory, and molecular orbital theory. So let's get into this. So the problem here says represent each of the following species by a Lewis structure and by the modified molecular orbital theory configuration showing pi bond electrons. And then in parentheses it says e.g. or for example, first use VBT hybridization to set up a skeletal structure for your molecule, then use MO theory, molecular orbital theory, to deal with the unhybridized p orbitals. So basically, I'm going to pretty much do the same thing I did in my last video. I'm going to show the Lewis dot structure. I'm going to show how the p orbitals are set up and how those will lead to pi bonding. Okay, so let's get into this. So I'm going to go ahead and draw the Lewis dot structures for each of these first. And then I'll go further into the unhybridized p orbitals and the pi bonds. Okay, so for ozone here, for the skeletal structure, I will go through the skeletal structure quickly. If you need help or need a review of how to do skeletal structures, or I'm sorry, how to do Lewis dot structures, see my videos on Lewis dot structures. I have a video where I go over the different steps, to go through, and I have videos that go through example problems, a plethora of example problems where I apply those steps. So if you need a review, go see those videos as soon as possible. Okay, so here, skeletal structures. So for the oxygen, each oxygen has a six, blanking on the word, six valence electrons because it's in group 6. So I have 3 oxygens, that's 18 total. So when I do my Lewis dot structure for oxygen, it's going to look like this. So I used 2 electrons in each of the bonds. Here, let me make this a little bit longer. Okay, so that's 2 electrons per bond. That's 4. I start with 18, so I have 14 left. I'm going to put lone pairs on my outer atoms. So that's 6 each. So that's going to be 12. So I used 12 in my outer atoms, 12 electrons. I had 14 left. That means I have 2 left over. So I'm going to put them here on my central atom. And then I double check to make sure everyone's happy with an octet, except for this middle oxygen. Everyone's happy except for the middle one. So I can take a lone pair from one of the oxygens on the outside and make a double bond. I'll go ahead and do it for this one here. So now I have a double bond. So that's the Lewis dot structure for ozone, which is O3. NO2 minus. So for that one, again, similar. We'll have N in the middle, 2 oxygens, like so. The nitrogen has 5 electrons, because 5 valence electrons, because it's in group 5. I have 2 oxygen again, so oxygen has 6 valence electrons, so I have 2 of those, so that's 12. Plus the 5 from nitrogen, that's 17. And then don't forget charges. If you have a negative charge on your molecule, that means you have extra electrons, so you have to add that to your total. If you have a positive, then you have to subtract that from your total. So this is a -1. I have 17 that I counted. I have to add 1 because of the -1, so that gives me 18 total electrons. I use 2 for each of the bonds, so that's 4. So 18 minus 4 is 14. I'm going to add lone pairs to the outer atoms, my oxygens. So there's my lone pairs. That's 12. So 14 minus 12 is 2. So I have 2 left. I'm going to put the lone pairs, the 2 electrons on my central atom as a lone pair. And now I used up all my electrons. Double check to make sure everyone's happy with an octet. Again, the central atom is not happy. So I'm going to take, again, a lone pair from an oxygen, and I'm going to make a double bond. So there's my Lewis dot structure for NO2 minus. Next, I have CH3CO2 minus. That's acetate. So I have my acetate ion here, C2H3O2. So here I'm going to have the 2 carbons bonded together. I have 3 hydrogens here, and I have 2 oxygens here, like so. So let me write the hydrogens in. Okay, so I have my skeletal structure. So how many electrons do I have? So I have 2 carbons. Carbon has 4 valence electrons. So that's 2 times 4 is 8. Plus I have 3 hydrogens, one valence electron per hydrogen. So that's going to be 8 plus 3 is 11. Okay. And then I have 2 oxygens. Each oxygen has 6 valence electrons. I have 2 of them, so that's going to be 12. So here I have 12 plus 11. That's going to give me 23. And then I have the negative charge here. That's a negative 1. So again, because you have a negative charge, you got to add to your total. So it's a negative 1, so I have to add 1 to my total. So that gives me a total of 24 electrons. And so here I have 1, 2, 3, 4, 5, 6 bonds. So I used 12 electrons, 2 electrons per bond. So I'm going to subtract 12 from the 24. That gives me 12 left. So next I'm going to put lone pairs on my outer atoms to give them an octet. So that's 1, 2, 3, 4, 5, 6. 3 lone pairs for that oxygen, and 3 lone pairs for this oxygen. That's 12. So I used up all of my electrons. Now I need to double check to make sure everyone's happy with an octet. And I have everyone's happy except for this carbon right here. It's only got 3 bonds. It likes to have 4 bonds. So I'm going to take a lone pair from one of the oxygens and create a double bond. So I'll take it from this one here, create a double bond. And so now I have my skeletal structure for CH3CO2 minus. Next, for D, I have this one here, so we'll go ahead and I'll give my some space down here. So I have C. This is going to be a carbon chain. Anytime you have kind of a molecule that's carbons and hydrogens, the carbons are linked together in a chain, and then the hydrogens are attached to each carbon. The way you want to read this is that the hydrogens that follow the carbon are connected to the carbon that they're following. So here, these two hydrogens are bonded to this carbon, the first one. This hydrogen is bonded to the second carbon. This hydrogen is bonded to the third. And then these two are bonded to the fourth. So that's how you kind of read the structure. Same thing here. If I had 3 hydrogens following this carbon, so they're bonded to this carbon. And then the oxygens follow this carbon, so they're bonded to the carbon. And then, of course, the carbons are bonded to each other, forming that carbon chain. So here, the 4 carbons are bonded to each other. These 2 hydrogens are going to be bonded to this carbon. Oops. Let me draw this better. So I got a hydrogen there. One hydrogen on that carbon, one hydrogen on this carbon, and two hydrogens on that carbon there. So I got my skeletal structure. So how many electrons did I start with? Let's count them out. So I have 1, 2, 3, 4 carbons. Each carbon has 4 valence electrons because carbon is in group 4. So that's going to be 4 times 4 is 16. So I have 16 electrons, valence electrons from the carbon. And I have 1, 2, 3, 4, 5, 6 hydrogen. 1 valence electron per hydrogen, so that's 6. So I have 16 plus 6 is going to give me 22. So I have a total of 22 valence electrons. For my skeletal structure, I have 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 bonds, 2 electrons per bond, that's 18 electrons. So I used 18 electrons. My total that I'm starting with is 22. So 22 minus 18 is 4. So I have 4 valence electrons left. So now I want to give an octet to the atoms here. And so you'll notice that each carbon only has four bonds. Or I'm sorry, 3 bonds. They want 4. I have 4 electrons left over, so I can put 2 lone pairs somewhere. So what I'm going to do is I'm going to put them on the outer carbons first. And so then these carbons are now going to have an octet, but these carbons do not. So what I need to do is I need to move lone pairs to create double bonds. And so these lone pairs here are the only lone pairs I have. So that means I'm going to have to use this lone pair to create a double bond here. And I'm going to have to use this lone pair to create a double bond here. Like so. And so there's the Lewis dot structure for this molecule here. And then last but not least, we have SO2. So I'll write down SO2 here. So again, I have sulfur and 2 oxygens. That's going to be bonded to the sulfur. And so the total number of valence electrons, sulfur, like oxygen, is in group 6. I have 2 oxygens, 1 sulfur, that's 3. All of them have 6 valence electrons. 3 times 6 is 18. I use 2 bonds, so that's 4 electrons total. So I'm going to subtract the 4 from the 18, giving me 14 electrons left over. So I'm going to add lone pairs to the outer atoms to give them an octet. So that's going to be the oxygens. So I have 3 lone pairs there, and now I'm going to put 3 lone pairs on this oxygen. That's 12. I have 14 left. Minus 12 gives me 2 electrons left over. So I'm going to put that on the sulfur. Now, again, sulfur here, the central atom, does not have an octet. So I'm going to have to move a lone pair. Again, I could do it from either side. We'll do it from this side just to be different. We'll change it up a bit. So I'm going to put a double bond there. So now everyone is happy with an octet. So the sulfur has 3 bonds, 1 lone pair. This has 3 lone pairs, 1 bond. This has 2 bonds and 2 lone pairs. So everyone's happy with an octet. So now we have all the Lewis dot structures. And so let's talk about hybridization, and then we'll talk about the unhybridized p orbitals and how they're used in the pi bonding. Okay, let's deal with hybridization and the unhybridized p orbitals. So let's start with our ozone. I'm going to do this a little bit one at a time. I'll have to erase a little bit, but I'll use this space here. So I'm going to have to do some drawing. Hopefully my drawings are going to be good enough. So don't criticize me. Don't judge me based on my drawings, but I'll try to do my best. So here for the ozone, the way you determine hybridization is you count the number of electron groups around an atom, and then you determine how many atomic orbitals you need to hybridize together from that atom in order to get the hybridization. And we add our atomic orbitals from lower energy to higher energy, like so. So here, let me move this over a little bit. So here we have S, P, and D. So if we have a certain number of electron groups and we take that same number of atomic orbitals, so for example, if I have a total of 3 electron groups around my central atom, then I will need 3 atomic orbitals to hybridize. So I start with the S and I add 3 together. So I have 1 S and 2 P's. So that would be sp2 hybridization. Okay, so that's how the hybridization works. And again, for electron groups, double bonds are considered 1 electron group, not 2. Triple bonds are considered 1 electron group, not 3. Right. So each lone pair is an electron group as well. So if I look at this oxygen here, I have 1 bond and I have 3 lone pairs. That's a total of 4 electron groups. So I would take an S, a P, a P, a P, hybridize those together, and I get sp3 hybridized orbitals. So I get 4 sp3 hybridized orbitals. And so this is going to be sp3. This oxygen has 1 single bond, 1 double bond. Each of those is electron group, 1 electron group. And then I have the lone pair. That's a 3rd electron group. So this has 3 electron groups. So I need 3 atomic orbitals to hybridize. So I'm going to start with the S. And then I add 2 P's. So it's sp2 hybridized. So sp2 hybridized. And then the same thing for this one. I have the double bond and 2 lone pairs. So that's going to also be sp2 hybridized. Okay, so when I draw my structure here, I'm going to have the oxygen in the middle, the oxygens on either side. Now these are going to be my sigma bonds. So here, and then I have the lone pair. Oops, I should have 3 lone pairs on that one. So I have the lone pairs, 3 lone pairs in this one. I have 1 lone pair there, and I have 2 lone pairs on this one. So I have my sigma bonds are represented by the lines. So all the lines in here are going to have sigma bonds. The only time you have a pi bond, if you remember, is where you have a double or triple bond. So anytime you have a bond between the atoms in your molecule, there's always going to be 1 sigma bond and no more than 1 sigma bond. Because remember, sigma bonds are the bonds where the orbitals from the atoms that are bonded together overlap along the axis, so right between where the atoms are. So that's going to be the sigma bond. You're always going to have one sigma bond. You're not going to have two or three. If you have a double bond, that means that one of the bonds is a sigma bond and the other one has to be a pi bond. If you have a triple bond, then one of them is a sigma bond and the other two have to be pi bonds. And the pi bonds are there because of a overlap of the unhybridized p orbitals on the adjacent atoms, the atoms that are next to each other bonded together. Okay, and I'm going to show that in the picture here so you know what I am talking about. Okay, so I have my sigma bond here, I have a sigma bond here. Again, remember this is sp2, sp2. These are sp2 hybridized because they took one s orbital and two p orbitals, which means that it left one p orbital behind. It's unhybridized. So each of these oxygens here have an unhybridized p orbital. Oops. Sorry about that. Okay, so if we're going to draw this, it's going to be hard to draw, but if you can bear with me here, I'm going to move this out of the way. So you're going to have an unhybridized p orbital here, right? Oh, let me use a different color. And let me clarify this a little bit. So if we imagine that this is in the plane of the board, that the lone pairs are in the plane of the board, and then if we draw this a little bit such that it is to scale, so this is going to be lone pair there. This is going to be trigonal planar, and then this is going to be trigonal planar. So let's try to draw that like so. Oops, this only has one lone pair. And then the bond is going to be like this with the oxygen there. I think this oxygen is bigger than the others, but that's just a drawing. Okay, so now this is sp2 hybridized, it's trigonal planar, and then this is sp2 hybridized, it's trigonal planar. And the way that the pi bonds are going to be working is with the unhybridized p orbitals, and the p orbitals are going to be perpendicular to the plane. So remember, the p orbitals are all at right angles of each other. So here, this is a planar molecule, this is trigonal planar, this is trigonal planar, and so the p orbital is going to come out of the board. So the way I'm going to draw that as best as I can, where the p orbital is kind of going into the board that way, and then the p orbital is, let's see, coming out of the board this way. Same thing with this one, so the p orbital is going to be going into the board, this one's going to be coming out of the board. I know it's hard to imagine, but hopefully this is the perspective here is correct. And so these are unhybridized orbitals. So then the unhybridized orbitals here, the p orbitals are going to overlap like so. And so this creates your pi bond. So here we have a sigma bond in the middle here, and then you have your pi bond, which is due to the overlap of the electron density of the p orbitals. So you have occupied p orbitals here that are unhybridized, and then you have that overlap, and this is going to then, you get your pi star, your pi bond star, your anti-pi bonds and all that, because remember, in molecular orbital theory, you're not hybridizing. Okay, so just to kind of talk a little bit about the difference between valence bond theory. Valence bond theory is where this hybridization comes in. That's where you're taking the atomic orbitals of one atom and hybridizing those on that atom. So those hybrid orbitals only belong to that atom. So here, for this oxygen, it's sp3 hybridized. So the atomic orbitals here are hybridized and belong to only this oxygen. So I took the s and 3 p orbitals from this oxygen, hybridized them, and I got 4 hybrid orbitals belonging only to this atom. So that's valence bond theory. But molecular orbital theory basically says, and we're talking about molecular orbitals. So when I talk about molecular orbitals here using valence bond theory, I don't mean the same thing when I say molecular orbitals in molecular orbital theory, because the molecular orbitals for valence bond theory belong only to the atom from which the atomic orbitals were hybridized. But for molecular orbital theory, the orbitals of different atoms are going to be kind of hybridizing. I don't want to use the word hybridizing, but basically the different orbitals from different atoms are then going to hybridize or kind of come together to produce molecular orbitals, and those molecular orbitals belong to the whole molecule, not just to one atom. So sp3, sp2, sp hybridization, sp3d hybridization, all of that belongs to whatever particular atom from which you use those orbitals, those atomic orbitals, to make that sp2 or sp3 hybridized orbitals, whatever the hybridized orbitals are. But here we have an unhybridized p orbital on each of these atoms. These guys are going to overlap to form an orbital, a molecular orbital, to house your electrons. So this is where the p, the pi bond is coming from. So you'll notice that you have you're kind of putting together or overlapping the unhybridized p orbitals on different atoms. And so that's what you're getting there. So that is your ozone. Let's go ahead and do the NO2. So if I do NO2, let me draw that here. Again, I have for NO2, this oxygen, just like this oxygen, is sp3 hybridized because I have 1, 2, 3, 4 electron groups. So I need to use 4 atomic orbitals. So for this oxygen, I'm going to take the s and the 3 p's of that oxygen, the atomic orbitals of that oxygen, and I'm going to hybridize them to create 4 sp3 hybridized orbitals that are going to occupy these electron groups. So this one is, again, sp3 hybridized. This nitrogen here is 1 electron group. Remember, the double bond is electron group, so that's going to be 1 electron group. The lone pair is another electron group, and the single bond is another electron group. So I got 3 electron groups. So I need 3 atomic orbitals to hybridize. So I'm going to take an spp. So that's going to be sp2 hybridized. And the oxygen, again, has 2 lone pairs and 1 double bond. That's 3 electron groups. So that is also sp2 hybridized. And so now I can draw my structure and talk about the unhybridized p orbitals forming the pi bonds. So just give me 1 second. Okay, so when I draw the structure just like this, I'm going to have, again, look, I have sp3, sp2, sp2, sp3, sp2, sp2. So it's going to have the same structure as this one. So here I'll have a nitrogen and that's going to be bonded to oxygen. And then this is going to be trigonoplanar as well, so that's going to be oxygen. This oxygen has 3 lone pairs. The nitrogen has a lone pair. And this oxygen has 2 lone pairs. And again, because these two are sp2 hybridized, that's going to be trigonoplanar. So these are going to be trigonoplanar. This is going to be trigonoplanar. And this is tetrahedral because it's sp4 hybridized. It's got 4 electron groups. But these are going to be in the plane. So if we pretend that the lone pairs are in the plane of the board, then again, the unhybridized orbitals, remember again, because this is sp2 hybridized, I took 2 p orbitals and hybridized them with the s orbital, leaving 1 p orbital unhybridized. So this nitrogen and this oxygen both have an unhybridized p orbital, and so that can create your pi bond. And so again, if I use a different color, I'll use green this time. We'll say that the p orbital, the unhybridized p orbital, is coming in and out of the board. So again, I'll try to draw this as best as I can. So here, that's going into the board, and that's going out of the board. And this is going to go here. That wasn't very good. Let's try this again. So this is going into the board, this is going out of the board, and then this is going into the board, and this is going out of the board. And so then this is going to overlap. So this lobe, these 2 lobes are going to overlap, and then these 2 lobes are going to overlap. And so you've got on the left and the right of this plane here, the lobes of the unhybridized orbital, so they're overlapping here. And so again, this gives you your pi bond. So you've got the 1 sigma bond in the middle between the 2 atoms, and you've got the pi bond that's kind of outside that axis. And so that's why it's called a pi bond, because it's not along the axis directly between the atoms, it's on the outside. So here we have 1 pi bond and 1 sigma bond. So that's your double bond here, and so on. So that is the way it looks from that perspective here. Next, we have CH3CO2. So if we look at this, each of the atoms here, this carbon, again, has 1, 2, 3, 4 electron groups. So it needs 4 atomic orbitals to hybridize. So we're going to have a S, an S, a P, a P, a P. So here we have 1 S and 3 P, so that's going to be sp3 hybridized. So sp3 hybridized here. I'll put that here. So sp3 hybridized. And for this carbon here, I have 1, 2, 3 electron groups. Remember, the double bond is 1 electron group. So here I have 3 electron groups. So I'm going to need 3 atomic orbitals, spp. So that's sp2 hybridized. sp2 hybridized. This oxygen here has 3 electron groups. That's also sp2 hybridized. And that oxygen has 4 electron groups, so that's sp3 hybridized. Okay, now that we've identified the hybridization, we're going to now have to draw our Lewis dot structure, kind of like we did here, and talk about the unhybridized p orbitals. Okay, so let's draw our picture. So since we have a single bond between these, and we have two groups here, and we have two oxygens here. So we'll draw this like so. This is sp2 hybridized, so that's going to be trigonoplanar. So these three are going to be in the same plane with that carbon. So these two oxygens, this carbon are going to be in the same plane. So I have this carbon here, and then I have the one oxygen there, the one oxygen there, and then I have the carbon, and we have three hydrogens. I can draw this. Let's draw this to kind of some sort of perspective so it looks more accurate, three-dimensional. So that's coming out of the board. That's going into the board, and that's in the plane of the board. Okay, so I have two lone pairs here, and that's going to be trigonoplanar, and I have four lone pairs, or three lone pairs here. And so we said this is sp3 hybridized, right? So this is sp3 hybridized, four groups. This is sp2 hybridized, and that's sp2 hybridized, and this is sp3 hybridized. So then we have a double bond here. So that double bond includes a pi bond. Again, the pi bond is due to the unhybridized p orbitals on both the carbon and the oxygen. So that's what we have here, sp2 hybridized, sp2 hybridized. So one unhybridized p orbital is on both the carbon here and the oxygen. And so if I draw that, that's going to cause me some pain. Okay, I'll try my best. So again, we're going to assume that this is in the plane of the board, and then that the unhybridized p orbitals are going to come out perpendicular to the board. So I have to kind of draw it with the best perspective as I can. And we'll try to do it this way. So here, that's going into the board, right, like so. We'll get this out of the way. And here, let me fix this. Like so. Fix this a little bit. Like so. And then this is going to come out of the board. This is going to come out of the board. I'm losing some blue marker, so hopefully you can see that well enough. And then of course, these are going to overlap on this side of the board, and then these are going to overlap on that side of the board. And again, please forgive the drawing, but hopefully that helps. If I can get another color, possibly, maybe if I do this one. So if I do orange on this side, maybe that'll make it better. So then this is coming out of the board. This here is going into the board, so it's perpendicular to the plane of the board. So again, we have our pi bond that's on the outside of the axis, and we have our sigma bond on the inside of the axis here. And so this is not going to have any rotation. Remember, if you have a pi bond, that's going to hinder rotation around that axis. around this axis here, there's plenty of rotation. So this can spin and rotate, but here, this can spin and rotate, right? Because there's freedom to rotate around this one, so this can rotate. We're going to assume that it's in the plane of the board right now for the sake of drawing a picture, but this can rotate as well around this axis here. But there's not going to be any rotation here because of the pi bond. Okay, next, let's move to the next one. Here we have this molecule here. We have two double bonds. We have 1, 2, 3 groups around this carbon. So this is sp2 hybridized. We have 1, 2, 3 groups around that carbon. That's also going to be sp2 hybridized. 1, 2, 3 around that carbon. So that's sp2 hybridized. And finally around that carbon. So all the carbons are sp2 hybridized, meaning that all the carbons are planar, are trigonal planar. Now, there's not going to be any rotation around these carbons, but around that carbon, there's going to be rotation. Okay, so let me go ahead and draw my picture, and we'll be right back. Okay, so when we draw this, we're going to have to draw this as clearly as possible. So here I'm going to have hydrogen there. Okay. And we'll have a hydrogen here. We'll have a carbon like so. And then this is going to be trigonal planar. So I'm going to have a bond going that way, a bond going that way. Well, here, let me fix this like so. Not the best drawing. Then we're going to have carbon and hydrogen. So we're going to have a carbon up here, hydrogen down there. Okay, and then this is also going to be trigonal planar. So then this is going to be carbon. Let's see. Yeah. I'm going to draw the carbon here just to give myself some space. And then this carbon is trigonal planar. Then I got carbon there and a hydrogen there. So hopefully you can see that each carbon has a trigonal planar shape. Okay. I'm going to move this, kind of make it more trigonal planar. Okay, so here we have a double bond, and here we have a double bond. So when we're drawing our pi bonds, again, this is sp2 hybridized, so we've got one unhybridized p orbital here. And again, we're going to assume for the sake of the drawing that this is in the plane of the board, even though it's not necessarily have to be in the plane of the board. And this is going to be in the plane of the board, even though it's not necessarily the case because we have rotation around this bond. So this can rotate. But for the sake of showing the drawing, we're going to assume it's all in the plane of the board. So this carbon and this carbon have an unhybridized p orbital, which is we're going to say is perpendicular to the board. So then it's going to have one unhybridized p orbital like so. and then this is going to be like that. So this is going to be on the other side of the board going into the board. This is on that side of the board. And then these two lobes are going to overlap on this side of the board, right? So this is on this side, this is on the other side. So they're straddling both sides, left and right. And then, so again, here, these two carbons are sp2, sp2. So they're missing, they have an unhybridized p orbital. So here, let me get another color. This might be better. And again, so this one's going to be like so. Again, forgive the drawing. So then on this side, we're going to have overlap. On this side, we're going to have overlap. So again, the idea is that this one is on the one side of the board going into the board. This is coming out of the board. And so you've got your p orbitals overlapping. And so you've got your pi bond. So this would be a pi bond, double bond, sigma and pi, and this would be sigma and pi. And so that's what the molecule would look like. And again, we have rotation around this bond, so this could rotate this way, this can rotate as well. But we drew it so that it's all in the plane of the board. So please, again, forgive the drawing. It's the best I can do. And last but not least, we have SO2. So this oxygen here has 1, 2, 3 electron groups. So that's going to be sp2 hybridized. The sulfur here has 1, 2, 3 electron groups. That's sp2 hybridized. And this oxygen has 1, 2, 3, 4 electron groups. So that's sp3 hybridized. And if we draw our molecule like so, we have an S, an O, and an O, and a lone pair. This oxygen has 3 lone pairs. This oxygen has 2. Like so. And again, oops, did I say, yeah, 2. So this is sp2 hybridized, meaning that it has an unhybridized p orbital, and this also is sp2 hybridized, meaning it also has an unhybridized p orbital. And so if we assume that this is in the plane of the board, then what this might look like is, I'm going to use a different color. So if this is going into the plane of the board, here, let me use green. So if this is going into the plane of the board, this is coming out of the plane, and this is going into the plane of the board, this is coming out of the board. So then these two would overlap on this side, on the inner side, and then these would overlap on this side here, creating your pi bond. So you have your sigma bond going right between the two atoms, and you have your pi bond on the outside of the axis. So that's your double bond. And then here you have your single bond, sigma bond. And that is how we can see the overlap, or where this double bond is coming from and where the pi bond is coming from. It's all about the unhybridized orbitals. Okay, and so you can see that from these drawings here, hopefully. Okay, so now let's go back to ozone, and we didn't talk about resonance, so you're probably wondering about resonance. So let's go ahead and talk about resonance a little bit. Let's go back to oxygen. Okay, so I mean, it's not oxygen. Let's go back to the ozone, and let's talk about the structure again. So if we use the valence theory, right? Let's go ahead and we're going to bond these together like so. And let's assume that the all of the oxygens that are sp2 hybridized. So we can get the conductivity here, right? So we can get this structure here. If they're all sp2 hybridized, then that would leave 2 lone pairs and a single bond for this one, a single bond and 2 lone pairs here, and 2 single bonds and a lone pair for the middle oxygen. And that would take care of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 electrons, because we have 2 in each bond and we have the 5 lone pairs. And so that would take care of 14 electrons. And if they're all sp2 hybridized, then that means that we have an unhybridized p orbital on this oxygen, an unhybridized p orbital on that oxygen, and an unhybridized p orbital on that oxygen. So the valence bond theory would take care of the sigma bonds, but if we use molecular orbital theory, that means that we have 3, let me use a different color, 3 unhybridized p orbitals on each of the oxygens. Let me put the lone pairs back. And so since the molecule itself, as we said before, has a total of 18 valence electrons, and we used 4 of them for the sigma bonding, that would leave 4 more electrons for the unhybridized p orbitals. And so these 3 p orbitals, using molecular orbital theory, can then be hybridized and create 3 molecular orbitals for the resonance, right? So we can get that resonance, and remember, for molecular orbital theory, the molecular orbital is belongs to the whole molecule. So all of the atoms, that molecular orbital belongs to all of the atoms according to molecular orbital theory. And so let me go ahead and draw a picture of that. And so the 4 electrons that we have, so these 4 electrons are going to be occupying the 3 unhybridized p orbitals. And because of molecular orbital theory, just like in molecular orbital theory, just like with hybridization, the number of orbitals that you put in are the number of molecular orbitals you get out. Since we have 3 unhybridized p orbitals, we're going to get 3 molecular orbitals. And they're going to have difference in energy depending on the nodes that they're having. Or so, for example, if there's no nodes here, if we do this in different colors, remember you could have positive or negative, right? So if we use different colors, let me use different colors here. So if I use green, right? So green is one color, red is another color, Christmas colors. okay? And then if they're all the same on top, right? So if I have all of one kind on top, like plus or minus, so if this is all plus and this is all minus, then these are going to be overlapping all together, right? So then I'll have overlap. There's no node, so I'll have overlap all together for the molecule. So this would be the lowest energy possible. So that would be a bonding pi bond or molecular orbital. So I could call that pi bond, right? So that would be one molecular orbital. I could get it where there would be a, instead of like this, I would have a node in the middle, right? So here, this would be a non-bonding situation, right? So I'd have a node in the middle. Something like that, right? Something like that. Or actually, let's flip this around. So here I have a different color on the bottom. So this would be plus and plus, minus and minus. So something like that. Or that would be a non-bonding situation. So here I'd have another higher energy non-bonding molecular orbital. Or I could have a situation where I have two nodes in between. Oops. So maybe I have a node in between here and a node in between here. And here I'd have, this would be flipped. This would be green. And this would be green. And I have red on this side. And so this would be your anti-bonding orbital. So this would be the highest energy, so your anti-bonding. And so then, according to molecular orbital theory, these would be the three molecular orbitals that we get from, oops, I forgot my red down there. And so these are the three molecular orbitals we get from the mixing together or the hybridization of the three atomic orbitals on each of the oxygens. That's, again, your unhybridized p orbitals. And so since we have 4 electrons not in the sigma bonds, we would fill that up here. So we have spin up, spin down, spin up, spin down. And so the electrons in the non-bonding are not going to have any effect on bonding order, like figuring out what the bond order is between the oxygens. So this one has no electrons in it, so that's not going to matter. And so here we have 2 electrons in 1 pi molecular orbital. And so that's going to be 1 molecular orbital. And we have 2 bonds. So that means that we're going to have to split this between the 2, right? So this would give us 1 bond, 1 orbital, I should say, split between the 2 of the 2 bonds. And so we're going to get a half of a pi bond per bond here. So since we already have 1 sigma bond each, right, that's going to be 1 sigma bond, 1 sigma bond, then that pi bond is divided between all 3. So we have this bond between those 2, this bond between those 2. So we're going to have to split this between the 2 bonds here, and then that's going to be a half of a pi bond. So the bond order would end up being 1.5, 1 sigma and a half pi, and this is going to be 1 sigma and a half pi, right? So that's how you can understand the resonance with respect to the bonding order given in molecular orbital theory. And we can apply this to the rest of this as well, because for our NO2, right, NO2 minus, we have resonance there. This double bond could be over here. We could do the same thing for this one. This double bond here, that could be shared, right, between there. And so we can figure out the bond order using molecular orbital theory. And we have that double bond that can be shared there. And we have this as well. So all of this can be likely explained again in this manner here. Let's talk about NO2 minus. Let's talk about that one next. So here we are with NO2 minus. So same thing here, exactly the same thing. So here we'll have our 3 atoms where they're going to be sp2 hybridized, leaving unhybridized p orbitals. And so again, in the same way, you could have all of the unhybridized p orbitals can be set up with positive on one side and all have a negative lobe on the other side. So this would be a bonding pi molecular orbital, right? So that would be the lowest energy. Or you could have the non-bonding where you have a node in the middle, and of course these would be flipped, right? So you'd have red on top and green on the bottom. So these would be opposite signs, right? So that would be non-bonding. Or again, you could have the nodes in the middle of the bonds here. And so then you'd have something like this. So you get the nodes in the middle, and that would be your anti-bonding molecular orbital. So these are the three different molecular orbitals that you get from the different combinations of the overlap of the orbitals, the unhybridized p orbitals on your atoms. And again, we're treating these orbitals like wave functions and waves, right? So you can either get constructive interference or destructive interference. And so this is what gives us the different energies of the different molecular orbitals. And again, we have 18 total valence electrons in our molecule, and 14 of them are used in the sigma bonding, right? So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 electrons for lone pairs, and we have 2 for each bond. So that's going to give us 14 total, or 14 used in the sigma bonding. That gives us 4 left over. And so we're going to put those into our molecular orbitals for the pi bonding. And so when we do that, you see the same thing as before. So here we have 2 electrons in our pi bond. We have 2 electrons in the non-bonding and 0 in the anti-bonding. So the non-bonding is not going to have any effect on bonding order. And so this is not going to have any effect on bonding order either, since we don't have any electrons in that molecular orbital. So again, we have 2 electrons in our bonding orbital, our pi bonding orbital. So we have a bond order of 1 here, but again, that has to be shared between the 2 bonds here. It's shared by the whole molecule. And so therefore, the 1 becomes a half. So the pi bond is shared 1/2 for both atoms for both bonds. So we have one sigma bond here plus a half of a pi bond on this side, and then we have one sigma bond here plus a half. So basically the pi bond is being shared across the whole molecule, giving half to each side. And so that would be 1.5 bond order again. And once again, we could do the same thing for this one. Again, this would be the same thing, right? We'd end up getting 1.5 by the same argument here. Same thing with this molecule by the same argument. This one here, this would be a bit more difficult. This would the number of molecular orbitals would be greater since we have more unhybridized p orbitals, right? Because right now we have 1, 2, 3, 4 unhybridized p orbitals. Therefore, we would have to meld those together, hybridize those together, and get out of that 4 molecular orbitals. And then we would have to set that up, plug in the atoms, and then figure out the bond order again that way. And so I hope this helps clarify what this question is asking. Again, sorry about the drawings. I hope this was helpful. If it was helpful, then by all means, like the video, share the video, hit that like button somewhere over here. Also, make sure you subscribe to my channel. Help me out here. Hit that notification bell somewhere up here, and make sure you click all so that way you can be notified by all the videos I put out. And finally, put a comment down below in the comment section. Let me know what you think. Ask me questions, get clarification if you need it. Also, if you have a problem or a question you need help with, or if you have if you have any questions, or if you have a comment or you want to share something, please do that down below. I would love to hear from you. If you have a topic you want me to cover, share that down below. I would like to do that for you too. Thanks for joining me, and have a great day.